right, here's the video that I promised you guys. So I wanted to do one more drawing a structure. You guys will be able to complete the rest of these on your own, but let's try to do phosphite ion. So first we're going to calculate the valence electrons. So phosphorus has 5, plus oxygen has 6, but there's 3 of them. And then we need to add on more, 3 more electrons. So 6 times 3 is 18, 19, 20, 20, 22, 23, 24, 25, 26 equals 26 divided by 2 equals 13 pairs. All right, so now I'm going to draw my central atom and then surround it by my outer atoms. So we have phosphorus. And I'm going to just draw it in a triangle at first before I determine exactly how it's going to be. Because remember, if there ends up being a lone pair of electrons on the central atom, that changes the shape a little bit. All right, so I have used 3. I have to use 13 pairs, so I'm going to start adding my pairs onto my outer atoms. So that's 4, 5, 6 pair, 7, 8, 9 pair, 10, 11, 12 pair. Well, I have 1 more pair left over, and I can't put it on any of the outer atoms, so I have to put that on the central atom. I guess I'll just throw it here. I know that's going to change the shape of my molecule. So now I'm going to have to go and look at my shape sheet. I have 1 central atom, I have 3 outer atoms, and I have a lone pair of electrons on the central atom. So I'm taking a look at the shape sheet. All right, here we go. 1 central atom. I had 3 outer atoms, and I have 1 lone pair on the central atom. So it's trigonal pyramid with a bond angle of less than 109.5. So it's going to be shaped with the lone pair on top, and that's going to be pushing those outer atoms away from it. So that makes this end up looking like this. We'll go like that. And then oxygen, oxygen, oxygen. And we still have to draw our lone pairs. All right, now what is the last thing you have to do if it's an ion? You need to do the hard bracket and put the charge, -3. Okay, the last part that I wanted to explain to you was whether or not an entire molecule is polar and not just a bond. So remember what we talked about in class. If this central atom is being pulled upon equally in both directions, like CO2 here, I don't know if you remember this drawing, we drew it way back up at the top. I'm going to scroll up and show you, but it's being this carbon is being pulled equally on both sides by the oxygen. So I'm going to show you. Hold on. Going up way back to what we did at the beginning. Where is it? Oh goodness, it was way up here. All right, this is CO2. So because this carbon is being pulled upon equally in both directions, we would say that there's no net dipole, which means that the electrons aren't being pulled in one direction more than they are in the other. Okay, these oxygens are holding on to the electrons equal to one another with respect to that carbon. So we would say that this is a nonpolar molecule because this molecule is evenly pulled. So I'm going to go, all right, so I'm going to scroll back down here and All right, here we go. So because this is being pulled equally on all sides, with the carbon being in the center and the oxygens being on the outside, being pulled equally, this is a non-polar molecule. All right, SO3. First thing you need to check is, are there polar bonds within the molecule? And yes, there are. This is your sulfur, and these are your oxygens, oxygens, oxygens. So they're definitely polar bonds. So this molecule could be polar. However, this sulfur is being pulled equally on all of the sides. And so because of that, this would be considered a non-polar molecule. Okay, now let's look at water here. So we have oxygen here in the center, and we have our hydrogens and our hydrogens. Okay, I don't know if you remember, but when we drew water, we ended up having the lone pairs of electrons on the central atom. Okay, so let's try to determine if this molecule is polar or nonpolar. Well, first, does it have polar bonds? I mean, it has to have polar bonds in order for it even to have a chance of being polar. So yes, it does have polar bonds. If you were to look at the periodic table, oxygen is more electronegative than hydrogen, so there are polar bonds there. So now, is the molecule polar? Well, the outer two atoms are the same, okay? However, when you have these lone pairs of electrons on the central atom, like this, oops, here we go. When you have these lone pairs of electrons on this central atom, it misshapes the molecule. Remember, it bends it, okay? And because of that, we would consider this molecule to be a polar molecule. Okay, now let's look down at these two tetrahedral molecules. All right, so for CCl4, first we're going to look and see, are there polar bonds? Well, if we have carbon in the middle and chlorines on the outside, chlorines, 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 okay, there are polar bonds in it, because if you were to look at the periodic table, you would see that chlorine is more electronegative, right? More electronegative than carbon, okay? So there's definitely polar bonds here. But in order for the entire molecule to be polar, it needs to be pulled not equally on all sides. But because these are all chlorines that are pulling away from this carbon, it is being pulled equally. So because all of the outer atoms are the same, this is considered a non-polar molecule. Okay, none of these chlorines are going to be pulling on this carbon any differently than the other. Now, this is another tetrahedral molecule. Okay, we have carbon in the center, we have hydrogen here, and then we have chlorines. Okay, this one would be misshapen. Okay, so these chlorines are going to pull differently on this carbon than the hydrogen would, okay? So because there is an unequal pull on the central atom, we would consider this molecule to be polar. Oops, polar. All right. I have the rules outlined on how to determine if a molecule is polar or nonpolar. If there's all nonpolar bonds, that means that the molecule is nonpolar. If there are polar bonds that don't cancel each other out, that means it's a polar molecule. Okay. If there are polar bonds that don't cancel one another out, it's a nonpolar bond. And then molecular polarity depends on both the polarity of the individual bonds and on the geometry around the central atom. Polar molecules will have an overall dipole, so like a positive and negative end, and nonpolar molecules have no net dipole. So that means that they just kind of cancel each other out with the directions when they're pulling all in the same, pulling in the directions equally away from the central atom. Nonpolar molecules are typically symmetrical, and the center of the plus and minus charge coincides. Okay. So I hope that helps. I'm attaching your homework and also the worksheet that we did today in class is available for you to finish up and turn in as your in-class worksheet. And I think I have it due at the end of the day 2 days from now, but yeah, check that out and make sure that you, once it's submitted, you take pictures, or once you're done with it, take pictures and submit it. All right, I'll see you guys next week. Thanks for hanging in there. And if you have questions, please email me.